Our next speaker is George Daddis, and George is the CEO of Omni-ID, and he's going to talk about the journey from industrial RFID to the industrial Internet of Things. And I am going to pass keyboard and mouse control if I can. Okay, you should now have control, George.
Okay, great. Thank you. Appreciate it, Mark. Welcome to the webinar. I really do appreciate you folks attending, spending time with us today. We do want to talk about industrial RFID and its migration to the industrial Internet of Things. I'm kind of giving away the conclusion right away with the title. Let's go ahead. First, what I'd like to do, though, is to give a brief introduction for you to Omni-ID in case you folks haven't heard of us before. We started out in the RFID space, squarely in the RFID space. We were the very first to introduce the on-metal RFIDs. In fact, we have the fundamental patents for that. In fact, most implementations of on-metal tags are utilizing some form or another of that technology. We've expanded that product line dramatically over the years. We are delivering tags to the oil and gas industry, Department of Defense, tracking all the United States Marine Corps goods. Out in India, we have the largest deployment of RFID tags in that country's history, tagging containers. So we're all over the world doing heavy-duty industrial industrial tagging. Now, we were tracking carefully the progress of RFID into manufacturing and noticed that it wasn't proliferating as much as we thought it should or could, and took a lot closer look and actually saw an opportunity in that marketplace. There were some important capabilities missing from the original conception of an RFID tag, and filling those gaps led us to create another division within our company. It's called the ProVIEW division, and that is essentially a IoT solution for moving materials around the factory floors of large capital goods factories. We utilize, of course, a lot of RFID technologies, but we built heavily on that platform to include things like e-paper and sensors and all the types of things that Mark has been talking about over the last half hour or so. So let's move ahead. Just a brief look at ProVIEW. So what was that hitch we noticed in factories? So manufacturers were indeed using RFID on containers and other racks and WIP, work in progress, and all sorts of things that flowed across the factory floor, and it was very, very good at tracking those items, information going up into the cloud, and analytics up there would be able to determine congestion and all that. But that's where the process ended. There was no real way to feed back that information in real time back into the floor. Factories in general do not like their workers to be outfitted with Google Glasses or laptops or scanners and things like that. They really want everyone hands-free. And that really gave quite a kind of an interruption, if you will, to the free flow of information there. In fact, what we saw in many cases were people putting paper tags over our RFID tags on those same containers. That obviously allowed us to think very clearly about what was needed here. And what we did was combine the best of RFID, the ability to track in real time and report up through connections or communication paths to a central analytics processing unit, and the best of paper, which is the ability for any worker to come up with any amount of training and be able to see immediately what needs to be done with that container, material, good, whatever it be that's in front of them, essentially creating smart containers. So the system's comprised of just a few things here. It's a very simple system to deploy, and actually we deploy it many times right in parallel with the paper processes that used to drive these things. And by the way, that is a remarkable fact. We have found through direct experience and have had that experience mirrored in a number of marketing studies that 90 to 95% of all material flows today in factories are still driven by paper. Maybe barcode, but paper. Very few real material flows are actually driven by RFID of any sort. And so obviously that's the opportunity. We replace those pieces of paper with these e-label tags, or ProVIEW tags as we call them. Lots of capability in these things. Obviously we have multiple radios, passive RFID if you don't want an active. We have active radios, Wi-Fi, and 433, accelerometers, temperature sensors, and of course, it's the featured on there is the e-paper display, along with some buttons and LEDs. And interestingly, we have these things priced fairly aggressively. We leverage our very high volumes in manufacturing to make these things cost tens of dollars, which are often a lot lower cost than the $50, $60, even $80 that you see a lot of active tag manufacturers charging for heavy-duty tags. So we pair this up, obviously, with some software to make it work for you. Hardware is great, but without a way to use it, it's really not too much more than the plastic that it's built around. What we did was to modularize the software architecture to allow you to put into place piece by piece different IoT-based flows for replenishment, picking, work instructions, et cetera, et cetera. And in fact, what we did by studying the factory floor carefully over time was to notice that with about 4 specific applications, replenishment, work instructions, picking, and container management or container tracking, we could cover 80 to 90% of all the dynamic material flows on the factory floor. And what's important here are 2 observations. The first is that while there are a lot of individual solutions for some of these problems, like container tracking or an RTLS system for that, or picking with a pick-to-light machine, et cetera, ProVIEW is the only one we know that will, in one set of infrastructure, actually cover all of those. So it really reduces significantly the amount of infrastructure and the number of independent systems you have to put in to cover a lot of these material flows. And this is one of the main values that we're seeing when we are in some of our enterprise contracts with the automotive industry, when we're picking up and doing real scaled rollouts. The second thing is that you can combine these things. Now, we all know that the industry is moving to just-in-time and now to just-in-sequence, which really means not only are you worrying about minimizing inventories, but you're actually worrying about split-second timing of the delivery of these parts. That means these interlocking material flows have to work together. And so oftentimes we'll have replenishment feeding the back of a picking center, which will automatically flow into a picking operation driven by ProVIEW tags. And as soon as that kit is made up from the picking center, it's often put in the container that can be tracked in sequence number right to the point of use on the factory floor, where it's being assembled into a car, which has custom instructions that are utilized by our or implemented by our work instructions. Everything sequenced, the sequence numbering traceable all the way back to the original replenishment that filled the supermarket or the picking center in the back there, all the way up to the manufacturing line that produces the end car, straight on through. And that's really kind of the magic behind ProVIEW and utilizing some of the best characteristics, we believe, of a true IoT system. Sensing, flows, everyone tracked, and everyone participating in the overall decision-making. Let's move ahead. So I mentioned that we're going to be talking about the evolution of RFID into IoT. Let's start with its beginnings. RFID, of course, that's one of those things, words that people use so often now they forget it is an acronym like SCUBA. But it does stand for Radio Frequency Identification, and identification is the key word here. That was its original purpose. We wanted a way to quickly sense the individual, serialized, unique in the universe identity of an object among a very, very large population of objects. Now, before we start jumping into whether RFID is IoT or a precursor or something different, let's talk about IoT first, and I'll make sure we understand clearly the concept, certainly as we define it. If you look on the internet and try to get a definition of the Internet of Things, the definition I provide here is pretty typical. They all vary, but basically massively parallel network of connected devices. So there's a lot of devices out there, and that's the first thing you glean from that. And they're connected and working in a very large peer network. That's another thing you glean from that. Imbued with sensors, modest processing, signaling capabilities, et cetera. So these things are smart. These little items out there working in parallel, each individually are smart at some level. And they work in a framework or a combined fashion, typically hierarchically organized. So in short, a profusion of simple devices working collaboratively. Now, getting a little bit more philosophical on you, these are actually the elements that a lot of people say are critical for intelligence. One of my favorite books of all time is Gödel, Escher, Bach by Douglas Hofstadter. He talks about the nature of intelligence there, but these are the 3 elements that he observes in complex systems that do amazing things out of very small pieces. Obviously, the human brain can be looked at one. The computer is another, right? If you ever stood and thought about what a computer can do, and then think about the fact that it really does it out of a very few set of operations and a bunch of zeros and ones, it's actually truly amazing. But it is that repetition, that collection, a very large collection of those simple processing steps, arranged hierarchically with feedback loops and dynamic connections that allows us to do this very rich set of operations. An Internet of Things, especially an industrial Internet of Things technology stack, looks more or less like this. I've seen a bunch of them, and they all have essentially these 3 layers, sometimes named differently, but basically the functions are outlined as here. The first, starting from the bottom, devices, right? You got to have, and this is what people often think of most, certainly us here, where we started out with RFID. You got to have those little devices sitting out there, mounted and often tightly integrated with some sort of object. So that refrigerator becomes a smart refrigerator. That container in the factory becomes a smart container, knowing where it is and that sort of thing. But that by itself is not good enough. You need to be able to communicate that information to your many, many peers sitting around you, kind of like a crowdsourcing. And that information is usually collected up at a data or analytics layer where even though some processing is probably done at the leaf nodes and the devices, that data and analytics layer itself will pull the power of all those devices working separately into a 1 + 1 = 5 type of equation where you get a lot more benefit of understanding how all those devices information can be put together into a much larger picture. Now, hierarchy has to play a role here, and in IoT, that's very, very true. If we think about RTLS systems, you can even envision a complete device communication and analytics hierarchy right there at the ground level. You have tags spitting out beacons all the time. That's the devices. Communication is the wireless. It could be BLE. It could be a 433. It could be 900 megahertz. Carrying those beacons to a central layer, typically a bunch of gateways, which then report all of those beacons up into a processing layer where you have a mini analytics and processing center collecting all the information from those beacons, putting together, and emitting essentially a location for the object. You know, a little bit of a reductive example here, but one I think that makes the hierarchy clear. And obviously from that little hierarchy there, you can view that whole RTLS system itself as a node which reports the end product here, a location of an object or many objects, up to the next layer, probably over an Ethernet. And so again, the process starts. You're going over a communication path reporting the location up to probably a central processing unit, maybe at the enterprise level, tracking the whereabouts of all your goods on the factory floor. And even then, that whole thing encapsulated in that one, let's say, line, can be one hierarchical element reporting through the factory, and then the factories collected together reporting to the enterprise. So this is often a repeated pattern you'll see in IoT, successful IoT deployments. So let's come back to the question of RFID. The interesting thing here is that RFID is growing immensely from beyond its original purposes of just supplying wirelessly and ID. In fact, it's outgrowing its name, I would argue. We're already, and have been for probably 10, 15 years, putting significant amounts of onboard memory onto these passive RFID devices. We've been doing a lot of work with sensors. We are, and output devices for that matter. We're driving e-paper and lighting LEDs right off of standard passive RFID tags, doing humidity sensing, right, that in our own labs here. Obviously, location tracking is an important element. So you're seeing that there is already, in the world of RFID, the ability and the technology to throw signaling and outputs right onto these passive RFID tags. So for me, the line is blurring, and in fact, whether RFID is actually IoT or not becomes a question of arguing whether gray is black or white. You know, it is a spectrum, and it becomes almost academic at some point. So let's start to take a look at the real goals of IoT, and that will actually start to motivate some of our thinking as to why we grew passive RFID tags into the, in fact, completely into the different end of the spectrum, into a true IoT device and embodied by our ProVIEW tags. Goal number one, and the simplest one of all, is identity and tracking. This is the one that started the whole thing off. We wanted to be able to find things. So I'm going to tie each of these goals to specific examples we might find in a factory floor, specifically in material flow. But the obvious example here is you might have a bunch of returnable containers transiting between the supplier and the factory, and one of the age-old problems for factory owners and material goods or supply chain officers is tracking those containers as they go out to the suppliers and making sure they get back on time. And the RFID enables them to assign a unique identity, so they know at Ford if they sent that container off to JCI or whether they sent that container off to some other tier 1 supplier, and they can track therefore its receipt back and know who is delivering them back and who's not. There's one simple example. Moving ahead. Goal number 2, object-specific sensing and signaling. So now that you've got a device on that, wouldn't it be nice to know more than just its ID? We refer to these things often as triggers as much as we do as sensors. An RFID tag can often be used as a trigger because passive RFID has such a short range, people are starting to use it as a proximity location trigger. Yes, I'm within 2 feet of my destination. But we have accelerometers, we have temperature sensors, and signaling is the other forgotten half. People often talk about IIoT as an input device, and we have found that is a fallacy, honestly. You're really only talking about half of the equation there. You really want to be able to feed back to that device all the interesting information you found and processed, and then to be able to signal changes so that you can optimize, correct for errors, or what have you. So for us, signaling is just as important as sensing, and that's why we do the e-papering, that's why we have the LEDs, et cetera, et cetera. Okay, so good real-world example there. If you want to find that one thing, so like I say, in RFID, you can actually take inventory and count things really quickly, but what if you want to find the one thing? The RFID tag you can use signal sensing and that sort of thing to get kind of close, but that's a crude methodology. What you'd often like to do is to have that object itself signal, and so many people are thinking about cost-effective ways of putting LEDs on tags. For us, in our ProVIEW tags, it's obviously very, very simple. We simply signal through the e-paper or the LED. This is the tag you're looking for. In fact, we use that signal for very rich things, a lot more than here I am. We'll use it to display work instructions, what needs to happen next, routing instructions, where the object needs to go and where it needs to be taken. And we'll eliminate errors by flashing through the tag let's say when the object has been taken to the wrong destination, or if it's over temperature or anything like that. So signaling is extremely important as well. Moving ahead. Goal number 3, if we can get the thing to flip. And there we go. Decentralization and reliability. Now, this is an important user characteristic that a lot of users don't actually know how to verbalize. What they want are systems that spread the intelligence out through in a very low-cost manner throughout their factory, and thereby, through that decentralization, improve the reliability and improve the ability to sense things without having an incredible amount of cost applied to each area. And also the ability to grow modularly and scale things very, very simply. You don't want to spend huge chunks of money just to add one more sensor. You want to be able to scale it piece by piece. In our ProVIEW world, the example I'll give here for reliability is one similar to one I gave earlier. We can use the location sensing of tags to flash the tag to the user to let them know when they brought the cart to the wrong place, and then in fact inform them as to where it needs to go. I can use the and there's many other examples like that, but in the interest of time, let's move forward here. Goal number 4, aggregation. So it is very important to be able to sense the condition of an object, don't get me wrong. It's also important to have that object be able to speak to the workers and other machines around it. But you do get a real synergy when you get the information from many objects all flowing together. We've encountered one factory where they had a number of steps to building gears. It was the hobbing, of course, and the polishing, and then they had a long heat treating cycle. More steps followed thereafter. They paper labeled their trays of gears to follow a path through this varied set of manufacturing steps. And, machines would go up and down, things would happen, we had tool changes that happened at various machines. Things were very, very difficult to predict ahead of time, but yet they had to create a scheduling algorithm that optimized the flow of all these different gears through all these different steps, each step with different capabilities and different process times, et cetera. And they had to do that because with at the beginning of the day, because with paper labeling, that was really the only chance they got to actually write out the full route of that, to have to engage an army of people to update paper labels as these racks flowed through this 40-acre factory after 8 a.m. was just an impractical thing. But let's think about it differently. If you could actually sense where every single rack was at all times, you wouldn't need complicated scheduling algorithms. You could just simply look at the queues of every work step that needed to flow, and of course have a recipe of what needed to happen. And at that moment in time when a processing step is finished, you will evaluate the simplest, shortest queue for the next processing step and simply send the tag there. And you can use information about other racks to help optimize the algorithm from even there. But even in this particular case, all we needed to know was the shortest queue to send these things to for the next step. And that really simplified the flow. Aggregation. Last goal, autonomy. Now, this is one that we really haven't fully achieved yet, but nonetheless, we are starting to put together some of the elements. And really, it's more of a human-machine collaboration when I talk about autonomy. A good example here, again, I'll use the example in ProVIEW tags, but one electronics manufacturer uses these magazines you can kind of see here on the right to store PCBs in their manufacturing flow. And they were using workers to move these things around the factory. Not too many steps, right? You go through the surface mount line, but then you go to the X-ray line, then you go to the finishing or the packaging where you put it inside a plastic shell typically. But they run many, many different boards and have many different, therefore, types of cartridges filled with different boards. And these things have to go through the different steps and different in sequences. So these cartridges tend to look alike, and they were not many, but still highly disruptive errors in bringing the wrong cartridge to the wrong place. And moreover, the machines needed to be set up for the right processing step. So we fixed all of that, of course, with the location sensing, making sure that the operator was signaled it was brought to the wrong place. But importantly, for this example, we had the tag communicate wirelessly when it arrived at the right processing step, the actual parameters that the machine needed to know in order to do the right processing on that set of PCBs. That was especially important in the X-ray machine, as you would imagine. So the worker no longer was producing those errors or manually putting in those steps, just bringing the item to the machine, set the machine up automatically. Automation. All right, let's turn it back and start talking about industrial Internet of Things deployments and where we are in that. Phase one is more or less behind us, I would argue, serialization. We're doing a pretty good job right now of knowing how to deploy systems to serialize things. A single RFID tag allows us to serialize and track a specific item. I would argue we're solidly here in phase two, assisted processes, where we're augmenting the human and in some cases stepping towards automation. We are doing object sensing and signaling. That's our business right now. We're doing large elements of decentralization and aggregation. We're just sort of touching on the automation aspects, but we're good ways into phase two. Phase three, I tongue-in-cheek call the singularity point. This is where we are not quite there yet. We don't have lots of different systems all interacting seamlessly together, and we'll talk about that a little bit more in a second. And certainly, we don't see the level of autonomy that implemented that I think is really in the potential of true IoT. And in fact, the word singularity right there implies one of the mathematical characteristics of a singularity is that as you approach a singularity, you have no way of predicting what will happen after that point of singularity. You'll hear physicists often talk about that in the Big Bang. They have no idea what happened before then. In likewise fashion here, when we achieve the true full power of a massive number of different devices connected together in control of a lot of our processes in our factories, we have really, at this point in time, no real conception of the power of those things can actually, achieve. Self-building factories, build factories that can reconfigure themselves and or build different devices. All things are possible in the coming decades here. I'm getting far ahead of myself, but those are the phases. Let's move ahead. But let's get back to Earth here. Phase 2. There's some really interesting things that we can do right now without even thinking of these science fiction scenarios here. We are seeing just through our ProVIEW deployments, but we also see in the literature, IoT is directly responsible for 30% more or more improvements, typically when it is implemented in replace of standard or traditional factory automations. We see that right down in picking systems. We see that in container flow management, et cetera, et cetera. It's reduction of labor, that 30%. It's a reduction in latency and time, that 30%. And it's a reduction in errors, which brings us to the second bullet here. Our electronics manufacturer noticed that when humans were running a process, they were able to achieve 3 sigma by working with ISO procedures, training, and all of that. They wanted to achieve 6 sigma. If you look in the literature, you'll find that humans are generally good for 3 sigma, not too much more. But if you put a human together with a machine, you actually are able to achieve 6 sigma. This is a human-machine collaboration. I described those examples with our view tags, signaling when the item is brought to the wrong place, but there's plenty of other examples. And you've been hearing, likely, if you're involved in factory automation, a lot about human-machine collaboration to achieve those goals as well. Commercialization, Mark did a very eloquent job of talking about how the connected nature of IoT enables services-based sales, where companies remain close enough to their product that they can offer standards of service and other types of deliveries that transform an object or a sale of mass into an actual service. So I won't dwell too much more on that. Deployments, because of that connected nature, the other really strong benefit is that your product is forever evolving and growing. And we do this already in ProVIEW. When we start developing new capabilities, the same set of hardware, the same set of infrastructure stands, but we start pushing out new features automatically right to the customer. Robustness, 5 nines, reliability, obviously scalable architectures have that self-healing. If we have a couple of containers with their tags that are smushed by forklifts or whatever it be, the benefit of the system doesn't decrease markedly. It's what we call graceful degradation due to failure. So it behaves very, very well in the face of errors. And then flexibility, as I talked about before, one of the main benefits of ProVIEW is that same tag on a container can be very flexibly deployed in a picking system, and the next moment that same tag could be used in work instructions, and the next moment it could be used to track assets in a finished goods inventory. So it's very, very flexible use of technology. All right, so let's pull ourselves back to RFID for a second here. How can RFID grow a little bit more to enable more of those phase 2 benefits that we just talked about? Well, let's talk about what it does really well first. Tag cost, I think, is really great in RFID. Omni-ID's average tag pricing has dropped from over $1 when we started to, in the dimes, tens of cents for the same functionality, 10, 15 meter on metal type tags. We're doing incredible things now, pushing the cost down. And the reliability, our packaging, and this is true across the industry, of course, is better than ever. We're essentially completely embedding RFID in solid chunks of plastic or in ceramics or other types of things that allow them to survive in incredibly harsh environments. Size is reducing. Passive RFID obviously has zero maintenance because of the battery that Mark talked about earlier before being missing. And this is actually one of the best examples of standardization I've ever encountered in my technical career. It is one of the strongest standards ever. You can literally take any passive RFID reader from any manufacturer and read almost any passive RFID tag. It just works. One of the very best examples. Now, passive RFID does have its challenges. It's expensive to put the infrastructure in. We need to lower the cost there. It doesn't have great read ranges. There have been lots of attempts to improve that without changing the fundamental nature of what passive RFID actually means, everything from battery-assisted passive to, other techniques. But it does still struggle with that a fair amount. Without batteries and without a lot of energy there, sensing is actually fairly limited. It can be done, but it's fairly limited in its capabilities. A good example is it is very hard to collect data when it's not being read in the absence of energy. You can, but it's hard. And effective user feedback, we've talked about that before, in the same way that sensing is limited, the ability to signal is limited as well. All right. Other enablers, energy harvesting. We've been doing a lot of work with that, and we've been very successful in deploying energy harvest circuits for doing more than just replying through RFID. Like I said, we've been doing LED and sensors and those types of things. But we're faced with a very hard cost barrier. A coin cell battery is anywhere from 10 cents to 20 cents. Now, yes, I am not counting the cost to replace that battery, but generally we found that if we can make a device last for 5 years, typically the device itself has an obsolescence around that period of time. So that very hard cost of 10 to 20 cents on a simple battery circuit provides a kind of a real difficult hurdle for most energy harvesting circuits to overcome. We do see it happening at some point, and we're actually pushing that barrier now. We're down around a quarter to 35 cents for some simple functions, and we're going to keep pushing it. You'll probably see some products, real market products, not just dilettante experiments that you have out in the market today. Active RFID is obviously one other answer to some of the problems that you've seen in RFID, but it does bring along the battery. And it does have a number of technical challenges. It's a lot more expensive, obviously, typically an order of magnitude. Our true active tags without the displays and all that are around $10. I know Bluetooth BLEs can go from $5 to $10, and we can make them that. In fact, we have some that are not industrial that go down to $5 as well. But it's costly, right? Even at $4 or $5, it's going to be a lot to put it on some devices. The other issue, however, is lack of standardization. BLE is starting to change that, and I think I'm looking forward to a lot more benefits from that standard, but certainly prior to BLE, it was a nightmare. And in fact, you had to buy entire systems end-to-end to make them work, readers, the whole 9 yards. Let's finish up here. Standards, that's extremely important here. There are, like I said, successful standards, but I think IoT is lacking in standards. If the one thing you hear in most IoT talks like this one, whether when they define it, whether I did or whether Mark did or somebody else following me, the sense you get is that it's not one standard, and that's absolutely correct. You know, unlike, let's say, Wi-Fi or Blu-ray discs, where if you read a bunch of papers and implement to those standards, it should just work. There's no such collection of papers that if you implement to those standards, you will guarantee interoperability with other IoT. There's a lot of work that's being done in this area. Industry 4.0 is a good example over in Europe, but by no means can anyone claim their success in this region. Let's move ahead. So the real standardization challenge. Let me finish up here with just a couple slides. One more. There's certainly data transport, and that's the part that people love to talk about because it's the easiest. You know, are we talking Wi-Fi, are we talking BLE, et cetera, et cetera? Well, we're largely solving that. And I would argue that we're largely solving the data transport layer as well. In other words, when we want to transport the location of the device, what language or protocols do we use? The real cool thing about Internet of Things is it borrows all those standards from the Internet. And that's one of the things that is driving acceleration of IoT devices is the fact that data transport layer is largely defined. It uses standards like XML, JSON, HTML, and in fact, one would argue the entire set of standards that drives the entire Internet, the ability for DNS and all those other addressing capabilities. RESTful interfaces are built on that, et cetera. So I'm going to argue that we're well on our way there on the data transport. Data semantics, it's the problem. In computer science, they call this a symbol grounding problem. If I design a system and I want it to work with another system, typically I have to call the guy who's designing the other system up and negotiate a set of interfaces. Or if that's impossible, I have to design a set of glue logic that makes those two systems work together. That, I would argue, is one of the most important things we can solve. Imagine, if you will, let me make this problem really concrete, that there's no such thing as a computer operating system or a network operating system. And let's say you wanted to design the Microsoft Office suite, right? So you want to design a word processor, you're on the team designing the word processor. Okay, you get the word processing program put together. But now how do you talk to the printer to print it out? Well, you can design no operating systems. Now you can design a print driver. Well, what if you want to start talking about cut and paste? Well, you got to go call the Excel team over there and negotiate an API. Or maybe you define an API that you claim is standard But you can bet the Excel team over there has defined a paste and cut and copy interface that they claim is standard. Now somebody's got to write some glue logic. Moreover, you got to talk about who sits in memory where. I mean, that operating system does that too for you. So now you got to call that Excel team and make sure that you operate on this portion of memory, they operate on that portion of memory, you share the processor in a nice way. It's obviously a nightmare. That, my friends, is the world of IoT today. There is no central organizing operating system in large-scale deployment. Right? What do we need to do? We need to have a ubiquitous, discoverable communications program, something that everyone can plug into. Like that wall socket on your wall. You can plug in any device into that wall socket, it just works. You got to define the data semantics. What does a location mean, truly? And how do I design a system so that it just gobbles up that data without customizing it to whoever delivered it? Deployment and life cycle is obviously a big part of it. The communications infrastructure, hosting all this, and of course security, as Mark mentioned earlier, is a big piece. A number of all those things, I would argue, have to go into a truly successful IoT backplane. Last slide. The really good news is a lot of work has been done here. So what you're hearing from me actually is lobbying for people to really get together and put together this IoT backplane idea and get it deployed, because we are the suppliers of data, and we really want to, we are putting tags on everything, and we want to give that data to somebody to work with in a ubiquitous way. So the players here, the really big ones, I would argue, are the right ones. The big players have the influence in the industry and, frankly, the tolerance to break the chicken and the egg problem, to put the investment in to get that backplane deployed before there's a commercial need for it quite yet. So the GEs, one of our investors, GE, is putting a lot of dollars into this with their Predict system, IBM, obviously. So I'm really quite excited about that. But you do have a number of other people beyond the IBMs and the GEs and Texas Instruments. I think people like ThingWorks, even open source is got its foot in the water. So I'm encouraged. But I think we should all be working towards finding and identifying a couple of IoT backplanes that we want to standardize on and becoming part of that overall community. And I would argue that more than anything else, I think that's the last slide here, that this would cause the vast and quick proliferation of IoT in our marketplace. You certainly have a proliferation of companies providing these very interesting, unique ideas. Let's get together, let's find a mechanism to work together, that operating system of IoT, and I think we're going to really see some truly amazing things. That's my talk. I'm sticking with it. I'd love to take some questions if you have any.
George, thanks very much. Terrific presentation. Unfortunately, we're running a bit behind schedule, so we're not going to have time for questions. What I'll do is I will forward you the questions that have come in, and you guys can respond to those offline.
All right. Very good. Thank you, Mark.
All right. Thanks a lot.